All right, we're going to go ahead and take a look at what is a mole. Now, a mole is going to be a way for us, different scientists, in order to measure amounts of particles, molecules, or atoms within a sample. So, a mole is going to be the same idea as any counting unit. So, some ideas and everything of a counting unit will be like 1 dozen, meaning 12. A ream is 500. And if we have 12.011 grams of carbon, that is equal to 1 mole of carbon. So our mole is just the same idea as a dozen or a ream. It is just a way for us to count a certain number of particles, molecules, or atoms. Now, a mole is going to be Avogadro's number. This is the same name that we give to the number that describes a mole. Avogadro's number is going to be 6.02 times 10 to the 23rd. So 1 mole is equal to this amount. And again, kind of repeating that idea, the mole is the same idea as any type of counting unit. Now, we are able to use the mole to describe different substances. So if I have 1 mole of iron atoms, that is equal to 6.02 times 10 to the 23rd iron atoms. If I have 1 mole of C6H12O6 molecules, that is equal to 6.02 times 10 to the 23rd C6H12O6 molecules. So again, really going back to that idea that a mole is just a number that we use in order to count a certain number of things that we have. All right, so we are going to go ahead and we are going to take a look at an example of how we use a mole in everyday life. So our first one is going to be find the number of moles in 162 grams of silver. So what we're going to do is that we are going to use our dimensional analysis in order to do this. Now, if we remember our dimensional analysis, the first thing that we're going to do is that we're going to start with what is provided to us in the problem. So in this case, we are provided 162 grams of the silver. So this will be 162 grams of the Ag. We're going to put it into the setup. Now, because I have grams of silver on top, this means that I need to have the grams of silver on the bottom. Now, what and everything is going to go here in order to relate our mass back to our moles is going to be the molar mass. So the molar mass of our silver is 107.8682. So this is the molar mass is 107.8682 grams of our silver. So this number that we get from the periodic table is going to go into this spot. So this is 107.8682. Now, our molar mass is going to be equal to 1 mole of that substance. So this of our silver is equal to our 1 mole of our silver. And this 1 mole is going to go on top. And then we are able to solve. So we are going to get 162 divided by 107.8682 in order to get 1.50 moles of our silver. Now, the reason that I stopped at 1.50 is that we have to take a look at our significant figures. If we go ahead and take a look at 162, this is 3 significant figures. And that means that our answer should also have 3 significant figures in it. So our 1, 5, and 0 being 3 significant figures. Let's go ahead and take a look at our next example. It is asking how many moles are contained in 1.5 times 10 to the 12th atoms of lead. So just like before, we are going to start with what is provided to us in the problem, which is our atoms of lead. So it will be our 1.5 times 10 to the 12th, and we're going to put atoms of our lead. Now, whenever we are writing this out, we do want to go ahead and put everything that we can into the setup because that's really going to help us with determining what is going to come next. So we have our 1.5 times 10 to the 12th atoms of our lead, put it into our setup. Because we have atoms of lead on top, this means that we're going to have atoms of lead on the bottom. So this will be atoms of our lead. Now, whenever we are converting from atoms to moles, what we're going to use is Avogadro's number. So we are going to use that 6.02 times 10 to the 23rd, and that is going to be equal to our 1 mole. Now, remembering that Avogadro's number is the same idea as a counting unit, so we are able to put anything that we need to behind this. So it is 6.02 times 10 to the 23rd, and in this case, I need atoms of lead, which is going to be equal to my 1 mole of lead. So this is going to be where the placing everything that we can into the setup is going to be really important. Is because it's really going to drive where we are going to go. Now the atoms of lead we're going to place into our setup. So the 6.02 times 10 to the 23rd, which is equal to that 1 mole of our lead. And then we're able to multiply and divide. So we get 1.5 times 10 to the 12th times 1 divided by 6.02 times 10 to the 23rd. And this is going to provide us our 2.5 times 10 to the negative 12th moles of our lead. Now again, we do have to be concerned with our significant figures. When looking at something in scientific notation, I'm concerned with only what we have out front, which is our 1 and 5. So this means I have 2 significant figures, which means that in my answer, I should also have 2 significant figures in it. Taking a look at our next question, it's asking us to find the number of atoms of 18.6 grams of our iron. So the first thing that we're going to do is that we're looking at what's provided to us in the problem. So the 18.6 grams of our Fe. We're going to put this into the setup. Now, if I look, this is my grams of the Fe, which means that down here in the diagonal, we're also going to have the grams of our Fe. So the grams of our iron. Now, whenever we have grams, we are going to be looking at the mass, which in this case is going to be the molar mass. So if I look on the periodic table, the molar mass of iron is 55.845 grams. Now, remembering that the molar mass is equal to 1 mole that we have, we're able to go ahead and place this into our setup. So the grams of the Fe means that this number will be placed into this bottom right corner, so 55.845, which is equal to the 1 mole of our Fe, which is going to go on the top. So this will be our 1 mole of our Fe. Now, what we may have noticed is that if I end right here, I'm ending in moles of my iron. But that is not what the question is asking us. We're asked to find the number of atoms. So we have one more step we have to continue on. Now we have the moles of the Fe on top, which means that I need to have a mole of our Fe down here at the bottom. So this will be our mole of our Fe. Now we are going to go from our moles to our atoms. And so what we are going to use is going to be Avogadro's number. So that 6.02 times 10 to the 23rd, in this case, it's our atoms of our Fe equal to our 1 mole of our Fe. Now, this mole of Fe is going to go into our bottom right diagonal, and what that is equal to, being our atoms of our Fe, this and everything is going to go on top. So this will go on our last spot that we need. So the 6.02 times 10 to the 23rd atoms of our Fe. And then we're able to solve. We are going to multiply the top. So we want to multiply everything on the top first, get the answer, and then divide it by the bottom. And so whenever we do that, what we are going to get is 18.6 times the 6.02 times 10 to the 23rd divided by the 55.845. And this will give us an answer of 2.00 times 10 to the 23rd. And that'll be our atoms of our Fe as the answer. Now double checking with our significant figures, we should notice that our 18.6 is 3 significant figures, meaning that the 2.00 also being 3 significant figures. Let's take a look at our next example. It is asking how many grams are contained in 3.02 times 10 to the 23rd molecules of carbon monoxide. All right, so the first thing that we're going to go ahead and do is that we're going to find what is provided to us in the problem, which is going to be our 3.02 times 10 to the 23rd molecules of our carbon monoxide, of our CO. Putting this into our setup, we have our 3.02 times 10 to the 23rd molecules of our carbon monoxide. Now, we are not able to abbreviate molecules because if we were to abbreviate molecules, it would end up as MOL, which is the abbreviation for a mole. So we are not able to abbreviate the word molecules. Setting this up into our setup, we have our molecules of our CO on top, which means that we are going to have the molecules of our CO on the bottom. So this will be our molecules of the carbon monoxide. Now, with the molecules, we are going to need Avogadro's number, that 6.02 times 10 to the 23rd. And in this case, it's going to be molecules of our CO equal to our 1 mole of our carbon monoxide. We have the molecules of CO, which means this number will go into the bottom right corner. 6.02 times 10 to the 23rd. That is equal to our 1 mole of our CO, which will go on top. So this will be our 1 mole of our CO. Now, we are not quite finished because the problem is asking for us to find our grams. So we are going to need to expand the setup one more time. So expanding the setup, we have the mole of the CO on top, which means that on our diagonal, we're going to need our mole of our CO. Now, in order to go from moles to our grams, we are going to need the molar mass of our compound. So, looking at our molar mass, we do have a compound, which is going to be our carbon and our oxygen. So, in order to calculate the molar mass, we are going to add up the individual masses. Carbon has a mass of 12.011. Oxygen is 15.999. We are going to add these together in order to get the molar mass of 28.01 grams per mole. So this is the molar mass, but the grams per mole doesn't really help us in this format, so we need to go ahead and to change this. So this is going to be the same as our 28.01 grams of our CO equal to our 1 mole of our CO. Now we have the mole of our CO, which we're going to place into the diagonal, our 1 mole of our CO. And then that is going to be equal to our grams of the carbon monoxide, which are going to go on top. This will be our grams of the CO. And that number being the 28.01. We are able to solve this. We are going to multiply the top, divide it by the bottom. We are going to get the 3.02 times 10 to the 23rd times 28.01 divided by 6.02 times 10 to the 23rd. And this is going to give us our answer of 14.1 grams of our carbon monoxide. So we're ending in grams of our carbon monoxide, which is what we want. And so this right here is going to be the final answer, that 14.1 grams of our CO. Now, taking a look at this example, we're going to calculate the number of molecules contained in 3.00 moles of water. So we have our 3.00 moles of water as what is provided to us in the problem. So we have 3.00 moles of the H2O. Putting this into our setup. Now we have the moles of H2O on top, which means that in the diagonal, we are also going to need our mole of the H2O. Now, to go from our moles to our molecules, we are going to need Avogadro's number, being that 6.02 times 10 to the 23rd. So 6.02 times 10 to the 23rd molecules of the H2O is equal to the 1 mole of our H2O. Now that mole of our H2O is going to go in the bottom right, which is our 1, and what that is equal to being the molecules. So our molecules of our H2O is going to go on top. So this will be our molecules of the H2O, being that 6.02 times 10 to the 23rd. And then we're able to solve. We're going to multiply the top, divide the bottom, so 3.00 times 6.02 times 10 to the 23rd. This will give us 1.81 times 10 to the 24th molecules of H2O. Now we are ending in that molecules of our H2O, which is what we want. So we know that this is our answer that we need. We have 3 significant figures to start off with, and we're ending with 3 significant figures as well. Taking a look at our next example, we are going to calculate the number of moles of 2.00 times 10 to the 23rd molecules or formula units of our sodium hydroxide. Now, sodium hydroxide is an ionic compound, which means that it is specifically called a formula unit, not a molecule. So we're starting off with our 2.00 times 10 to the 23rd formula units of the sodium hydroxide. So I'm going to abbreviate formula units as Form U, and our sodium hydroxide is our NaOH. Putting this into the setup, we have our formula units of our sodium hydroxide on top, which means that we're going to need our formula units of our sodium hydroxide on the bottom. Now, same idea, even though it's formula units and not molecules or atoms, we are going to use Avogadro's number in order to go from our formula units to our moles. So we have that 6.02 times 10 to the 23rd, and in this case, our formula units of our sodium hydroxide equal to the 1 mole of our sodium hydroxide. That formula unit of our sodium hydroxide will go on the bottom. So the 6.02 times 10 to the 23rd, and that is equal to that mole of our sodium hydroxide, which will go on top. So that 1 mole of our NaOH. And then we're able to solve. We're going to multiply the top divided by the bottom. So 2.00 times 10 to the 23rd times 1 divided by the 6.02 times 10 to the 23rd. And this is going to get us our 0.332 moles of our NaOH. We are ending in moles of our NaOH, which is what we're asked to find. So we know that this is the correct answer. And if we take a look at our significant figures, we have 3 significant figures to start off with, and we are also ending with 3 significant figures. Taking a look at the next example, we are going to calculate the mass of 1.20 times 10 to the 23rd molecules of fluorine. So we are starting off with the 1.20 times 10 to the 23rd molecules of our fluorine. So we have our 1.20 times 10 to the 23rd molecules of the fluorine, which is going to be our F2. Now, our fluorine is a diatomic. So whenever we have fluorine, it is going to be our F2, meaning that we have 2 of the fluorine atoms. Now that we have the molecules of our F2 on top, that means that we are going to have the molecules of our F2 on the bottom. So our molecules of the F2. Now, whenever we have molecules, atoms, we are going to be using Avogadro's number. So that's 6.02 times 10 to the 23rd molecules of our F2 equal to our 1 mole of our F2. We have the molecules of our F2 on the bottom at 6.02 times 10 to the 23rd. And that's going to be equal to that mole of our F2, which is going to go on top. So our mole of our F2 will be on top. Now that we are in moles, we're able to convert this over to our mass. And whenever we are talking about mass, we are going to need the molar mass. Now our mole of our F2 is on top, which means that the mole of the F2 needs to be on the next diagonal. But calculating out our molar mass, we have our F2. Fluorine by itself has a mass of 19.00. We have 2 atoms of it. So all we have to do is 19.00 times 2 in order to get 38.00 grams per mole. Now, rewriting this in order to fit it into our setup, this is our 38.00 grams of our F2 equal to our 1 mole of our F2. This mole of our F2 is going to go into the diagonal, our 1 mole of our F2. And then what that is equal to, which is our grams of our F2, that is going to go on top. So what we're trying to solve for being our grams. And now we are ready to solve. We're going to multiply the top. We're going to divide by the bottom. So we are going to end up with our 1.20 times 10 to the 23rd times 38.00, all divided by the 6.02 times 10 to the 23rd. And this is going to give us our mass of the fluorine, which will be 7.57 grams of F2. We are ending in the grams of our F2, which we know that we're trying to solve for because that is going to be our mass. We need to look at our significant figures. We have 3 significant figures that we're starting off with, and we are also ending in 3 significant figures as well. Taking a look at the next example, we are going to calculate the number of hydrogen atoms in 15.5 grams of our tricarbon octahydride. So we are going to be starting off with our 15.5 grams of the tricarbon octahydride. So creating the formula for this, I have tricarbon, meaning I have 3 carbon atoms, octahydride, hydride being the hydrogen, octa meaning I have 8. Starting off, we have the 15.5 grams of our C3H8. Putting this into our setup, we have the grams of our C3H8 on top, which means in the diagonal, we are going to need the grams of our C3H8. Now, whenever we have grams, we are going to be using the molar mass. So we need to go ahead and calculate the molar mass of our C3H8. So carbon has a mass of 12.011. Hydrogen has a mass of 1.008. In the tricarbon, I have 3 carbon atoms. The octahydride, I have 8 hydrogen atoms. So we are going to get 12.011 times 3 to give us 36.033. 1.008 times 8 is going to give us 8.064. We're going to add these together in order to find the molar mass of the compound, which will be our 44.097 grams per mole. Now putting this into the format that we're able to use, this will be our 44.097 grams of our C3H8 equal to the 1 mole of our C3H8. We have that grams of our C3H8 ready to go. So that will be our 44.097. That is equal to our mole of our C3H8, which will go on top. Now, ending in moles, We're not quite finished, so we need to go ahead and continue on. We have the mole of our C3H8 on top, so we know that in the next diagonal, we're going to need our mole of our C3H8. Now, going from our moles over to our molecules, we are going to use Avogadro's number. So the 6.02 times 10 to the 23rd molecules of our C3H8 is equal to our 1 mole of our C3H8. This mole of our C3H8 can be placed in the setup. And then we have our molecules, which is what this is equal to, and that will go on top. So the 6.02 times 10 to the 23rd molecules of our C3H8. Now, specifically in this question, it is asking us to calculate the number of hydrogen atoms. So we are not finished because we have now just calculated our molecules of our C3H8, but it's asking for our number of hydrogen atoms within that molecule. So this one is going to have an additional step to it because we're looking specifically for the number of hydrogen atoms. So we are going to expand this only one more time. Now we have the molecules of our C3H8 on top, which means that in the diagonal, we're also going to need our molecules of our C3H8. Now, what we have to look at is that whenever we have a molecule of C3H8, so let's say that I have one molecule of my C3H8. Within that one molecule, how many hydrogen atoms do I have? So whenever I have one molecule of the C3H8, this is going to be equal to my 8 hydrogen atoms. So within one molecule of my C3H8, I have 8 hydrogen atoms, and I'm able to use that in order to solve for my number of hydrogen atoms overall. So we have that molecules of our C3H8, so within one molecule of the C3H8, we're able to solve for the hydrogen atoms. And this will be our last step, which is going to go on top. This will be our 8 hydrogen atoms. And then we're able to solve. We're going to multiply the top. We're going to divide the bottom. So we're going to get 15.5 times 6.02 times 10 to the 23rd times our 8 hydrogen atoms, all divided by 44.097. And this is going to get us 1.69 times 10 to the 24th atoms of hydrogen, or our hydrogen atoms. And this right here is going to be our answer. Now, again, we are ending in those atoms of hydrogen, which is what I'm trying to find. If I take a look at the significant figures, I have 3 significant figures, which is what I'm starting off with. And I'm also ending in 3 significant figures as well. And that is going to be how we take a look at calculating the number of atoms whenever we're provided the mass of a compound.